Before I can define quadrilaterals, let me define a polygonal path. So for this particular polygonal path, we're going to start with 5 different points. And we're going to label these P0, P1, P2, P3, and P4, and these points can be anywhere in the plane. We're then going to draw a line segment from P0 to P1, a segment from P1 to P2, P2 to P3, and then P3 to P4. And this here is known as a polygonal path of order 4, in particular because there's 1, 2, 3, 4 sides. So the points are known as the vertices and the segments are called the sides. We really want to consider closed polygonal paths of order 4. So in this case, P0 is equal to P4. So here I have my points P0, P1, P2, P3, and P4 will be the same as P0. So when I draw my segments, I go from 0 to 1, 1 to 2, 2 to 3, and then 3 to 4. As another example, I can put P1 here, or P0 here, P1 here, P2 up here, P3 down here, and then once again do P4 as P0. I then go from 0 to 1, from 1 to 2, 2 to 3, and then 3 to 4. So both of these would be closed polygonal paths of order 4. This one here on the left is known as simple since it doesn't intersect itself. This one on the right is not simple since it does intersect itself. Now that I have this idea of polygonal paths, I want to define a quadrilateral, ABCD. And a quadrilateral is going to be a simple closed polygonal path where my 5 points are A, B, C, D, and then A again since the last point needs to match the first. We also need the property that no 3 of my vertices are collinear, so any 3 vertices should not lie on a straight line. A really important property of quadrilaterals and in general polygons is to be convex. So what does it mean to be a convex quadrilateral? In order to be convex, it means the closed half plane determined by any of the sides completely contains the quadrilateral. So if I look at a couple of examples, this one here will be convex because if I extend out any one of the sides, not a great extension, but we see that the entire quadrilateral is on one side of that line. If I extend this one out, the entire quadrilateral is on one side of that line. However, if I look at something like this quadrilateral here, we can see that we still have 4 points. However, if I try to extend out this side right here, it breaks the quadrilateral into 2 pieces. This piece over here, and then this piece over here. So this one over here would be not convex. Looking at the idea of congruence of quadrilaterals, my first particular property is going to be SASAS. So let me go ahead and draw 2 quadrilaterals. Here's the first, and then my second will be over here. And we'll assume, although I did not draw them perfect, we will assume that these are approximately congruent. For SASAS, I need a side to be congruent, the next side to be congruent, and then the third side. So I need 3 sides in a row to be congruent, as well as these 2 angles here. So 3 sides and the accompanying angles that go between them. While I won't won't directly write down this proof, I will discuss the idea. Essentially, I'm going to break these two into some smaller triangles. These lower triangles here have a side, an angle, and a side congruent, so by SAS, these are congruent, which means this side here is congruent to this side here. In addition, this angle 1 is congruent to this angle 2. So we have angle 1 is congruent to angle 2. Well, since this larger angle and this larger angle are the same, that means that 3 and 4 have to be congruent. That then gives us these two upper triangles are congruent by side, angle, side, which then guarantees my fifth side, or my fourth side is congruent, as well as this angle here. I also knew this angle up here and this angle down here were congruent. I also have the other pieces, so I have that these angles are all congruent. Should have 4 and these should have 3. So the idea is to break it up into smaller triangles and use my triangle equivalences to show appropriate pieces work. I also have the idea of ASASA. So let me once again draw another picture. And we'll draw the second version as well. This time I need 3 of my angles to be congruent. And the sides between them to be congruent. And I won't directly go through the proof of this one or drawing the picture, but the idea is the same. Break it up into 2 triangles that you show are congruent. And so we use the idea of corresponding parts to get that these entire quadrilaterals are congruent.